All right, thank you. Yeah, so my name is Jan and I am finishing up my PhD here at the University of Amsterdam. I do realize there's somebody making a hole in an apartment next door, so I hope you guys will be able to hear me over this person. But I'll be presenting on a project that actually spawned after the previous PinT workshop. So last year I spoke about adaptivity for parabolic PDEs in a space-time setting. It was actually kind of close to what Johannes was talking about. And I effectively made the case against parallel computing in favor of local space-time adaptivity. But after the talk, my academic brother Raymond and we got the idea that the exact same algorithm might actually work well in a parallel setting. And we got to work, and the results of this project are actually in the proceedings of the previous PinT workshop. So that's quite nice. So the topic of today will be a couple further thoughts on this. Okay, so space-time residual minimization. We already saw from Johannes' talk basically the same introduction that I was going to give, but we have some spatial domain omega, some time interval, some elliptic operator A, and we want to solve this parabolic PDE subject to an initial condition and with some boundary conditions. So you could think about A as being the negative Laplacian, in which case you have the heat equation, or maybe some more difficult operator, or maybe you have a plate bending problem. These are all kind of parabolic problems that fall into this framework. And we're going to solve these problems numerically through a process we call space-time residual minimization. And this was introduced by Roman Andreev in 2013. So if we have delta some discretization parameter and some corresponding finite element trial space x of delta, then we are going to balance the residuals both in this equation and in this equation. We're going to make them both. We're going to look for that solution, the minimal residual solution that makes both small, essentially. And as we saw from Johannes' talk, this has a couple of nice properties. Firstly, we have this quasi-optimality, which means that the error in your solution is, up to some constant, the best error you can get from your trial space. And we can do space-time adaptivity, as we already saw. And for this particular method, we can also devise optimal preconditioners. And it turns out this method is even suitable for some ill-posed problems, such as a data assimilation problem. And you basically just add extra terms to this thing, maybe some data terms, whatever you also need to get small. But as it is a space-time method, it's very easy to use this in a parallel setting. And that's exactly the topic of today. So let's take a look at some complexity results. So we all know the serial complexity of an algorithm is its asymptotic runtime in terms of the size of the input on a single computer, a single core. And if we discretize some PDE with n unknowns, if you're looking at a serial computer, then solving it in linear time is optimal, because you need to set up the right-hand side of the linear system. For instance, you can't be faster than linear. And for elliptic PDEs, if you look at uniform refinements and assume that the error, the discretization error decays algebraically, which means that u minus its discretization is basically order n to the minus s for some s greater than 0, then you can show that preconditioned CG plus a multigrid preconditioner and nested iteration has this nice linear complexity. And nested iteration basically means that you start your CG iteration at the course's mesh, and then alternate some steps of PCG with a prolongation, some steps of PCG prolongation. And in doing so, you reduce the cost of the early PCG iterations. And this drives down the complexity from n log n to order n. So now a little bit more for an idea. So we define the parallel complexity of an algorithm as its asymptotic runtime given enough cores and assuming that there is no communication cost. So essentially you have this infinite sized multi-core processor and they all share some infinite size memory. Some infinite size memory. And within this ideal situation in 1991, Worley showed the theoretical lower bound of order log n. So there is no way of solving a PDE numerically faster than order log n on a parallel computer. But it turns out that this is indeed a theoretical result, because for elliptic PDEs, the best known practical algorithm is only log squared of n. So it's slightly worse. And this was achieved by Aki Brandt in 1981 by combining preconditioned CG and this nested iteration with a parallel multigrid preconditioner. And then in 1995, Horton, van der Walle, and Worley asked, so this is a direct quote, are good serial algorithms for parabolic PDEs intrinsically as parallel as good serial algorithms for elliptic PDEs? Or, paraphrased, can we achieve this order n and order log squared n also for parabolic PDEs? This is basically the setup for today's talk. So, we are looking at tensor-product discretizations for linear parabolic PDEs, and we have NT versus NX unknowns in time and space. Then the well-known parallel algorithm basically alternates a coarse grid solve in serial and then a number of fine grid solves in parallel or parallel in time. And you basically iterate this process, and every iteration has a time parallel complexity that's the square root of n in time if you balance the number of fine grid solvers with the size every solver has to do. So in 2019, Martin Neumüller and Ian Smears, they introduced, they reinterpreted an implicit Euler scheme as a space-time method, basically building a gigantic linear system. And they solved this using inexact Uzawa and some Fourier transform in time as a preconditioner. And because of this FFT, every iteration of their iterative process has this superlinear serial complexity. This n log n is of course due to the FFT. And then these two complexities. So logarithmic complexity if you look at a parallel in space and time. So our idea was to, well, it was more than that, but essentially swap out the FFT for a wavelet transform, because we know that the wavelet transform is can be done at linear cost, right? So every iteration of our algorithm in serial has a linear cost, and in parallel has a logarithmic cost. And taking ideas from this elliptic PDE community, if we take uniform refinements and assume this algebraic error decay, then we can do the entire solution process indeed in linear cost on a serial machine and log squared cost on a parallel machine. And this, as I said, is on par with the best known result for elliptic PDEs. But this is not the whole story, because the algorithm turns out to be actually efficient in practice as well. All right, so we'll kind of go through this at a bit faster pace because I think Johannes gave us a good taste of it already. So we have the parabolic PDE. We have some Gelfand triple of spatial functions, V embedded in H, embedded into the dual of V. So we think of H being L2, V being H10, and A being the negative Laplacian, if we are looking at the heat equation, for instance. And so here, A is just some linear bounded coercive differential operator, right? And then the space-time variational form is to find U in some space X of space-time functions so that when tested against all functions v in some other space y, this holds. Yeah. So as opposed to Johannes' talk, we are not going to reformulate this as a system of first order equations. We're going to just treat it as the second or fourth order problem that this is. So in 2009, Christoph Schwab and my advisor Rob Stevenson, they proved that if you take X to be this intersection of Bochner spaces and Y this other Bochner space, then this funky operator is a bounded linear operator, but it's also invertible and it has a bounded inverse. And this exactly means that finding U of X that solves these two equations is a well-posed problem. So that's a good foundation for us to start doing some functional analysis. So we want to find this minimal residual function given some family of discretizations or of discrete round test spaces. So delta will always mean the discretization parameter, and this capital delta will be the entire class family of discretizations. So it is fairly well known that these kind of problems usually end up involving some inf sub stability constant. Indeed, also for our method, we have this this LBB constant that involves the operator B and the trace operator. And this is a kind of difficult stability estimate to show. Johannes indeed already told you guys so. So Andreev in 2013 and Andreev back in 2013 showed for the heat equation, and we generalized this to arbitrary linear parabolic PDEs quite recently. We showed that this inf sub stability can be guaranteed when your trial space is embedded in the test space and you have some inf sub stability with respect to the time derivative only. So that's much easier than the entire parabolic operator. Okay. And furthermore, in this case, our minimal residual solutions are quasi-optimal. So that means that the error that you incur in the solution that you find is actually bounded by some constant multiple of the best error that you could, that your trial space allows for, right? So this is quasi-optimal. It's almost the best you can expect. But this minimization process, and especially this dual norm, is kind of difficult to construct. So how do we practically compute this thing? Well, you can see that this minimal residual solution solves some normal equations. But in here you have the inverse of a Ries operator, and that thing we can't compute. So Johannes' solution here was to make a quasi-optimal test space. What we do is we replace this thing by a preconditioner, and then we end up with a practical system that we can solve. And it's actually, if this thing is an optimal preconditioner, it's an equivalent system. So with some abusive notation, we end up with this system S delta UMR equals F delta that we want to solve. And the idea for the remainder of this talk will be to write this system with respect to a wavelet in time, finite element in space basis, build some optimal preconditioner, which we're then going to solve in parallel very effectively. Okay, very quickly maybe. So we have here time and space, some initial discretizations, and we're just going to do red refinements both in time and space. And then we're going to overlay for our trial space, temporal trial space, a polynomial, piecewise polynomials of certain degree, and in space, piecewise polynomials of some other degree with some built-in boundary conditions. And then at our test side, we're going to take discontinuous piecewise polynomials. And if we take our trial space to be the tensor product of this kind of space with this kind of space, and our test space to be the tensor product of these two spaces, then it turns out that this family of tensor product spaces is indeed M-sub-stable, which means that we have this powerful theorem of quasi-optimality. In layman's terms, this is what we want, like we are in business. So we are going to equip our spaces with finite element bases, and then we have the matrix form of our practical system. So S U equals F, and this S consists of a number of operators, of which B and this gamma naught are both uniformly sparse, meaning that they have a constant number of non-zeros per row and column, independent of the discretization that you would have. And K here, the preconditioner K, is a block diagonal operator with multigrid in space blocks. Okay, so we want to solve this thing, but we need a preconditioner. But we can build a preconditioner in wavelet space. And it turns out, removing the technicalities, that we can build a wavelet to single scale transform. We can equip this base, well, we can equip the trial space with a different wavelet in time basis. And then we get a different system, but the wavelet in time and the finite element in time systems are related. And we can actually build a preconditioner for this wavelet in time matrix. And again, as a block diagonal operator with multigrid in space blocks. Okay, so I think I need to speed up a little bit, but this is quite important. So we are going to run preconditioned CG on this system, and we're going to start with initial guess 0. And as we have an optimal preconditioner, every PCG iteration decreases the algebraic error by a constant factor. And so in order to reach some target error epsilon, we need order log epsilon inverse iterations of PCG. And so if we have a fixed target error epsilon, so not dependent on the discretization at hand, then the number of PCG iterations is also independent of this discretization. Okay, so now let's look at the complexity. We're back at the start. We have the serial complexity, the parallel complexity, and if we write n of t for the dimension of our trial space in time, n of x for the dimension of our trial space in space, and n as its product, then in every PCG iteration we apply basically 4 matrices, and we're going to look at their complexities. So this normal equation, the practical system matrix, consists of these couple matrices, and this B and gamma naught are both uniformly sparse, right? We have a constant number of non-zero per row and column. And this means that if you apply them in parallel, then you can apply them at constant cost, because you can basically assign one or a couple processors to every cell in the matrix, because we are in this idealized parallel setting where we have an infinite number or enough cores at our disposal. Okay, and we have these two block diagonal matrices with multigrid in space blocks. And well, multigrid is we can apply these matrices on a serial computer in linear time, and on a parallel computer in logarithmic time, logarithmic in space even. And this is a sort of intuitive argument, but in a uniform discretization, you have a logarithmic number of multigrid levels in your hierarchy. You can apply each level at constant cost, so your entire cost is logarithmic. And then we have the wavelet transforms. And of course, it's a well-known result that the fast wavelet transform is linear in serial. And it turns out that it's logarithmic in parallel. So every iteration of PCG is basically the sum of these costs together, and you end up with this schematic. And because if we fix the target algebraic error epsilon as a constant, we have a constant number of PCG iterations. Therefore, its complexity is the same. But this is not the full story. As I said before, we're dealing with an iterative process, right? So we have our current estimate UK, and the error in UK turns out to be related to the sum of the discretization error and the algebraic error. So this is the error. This is how far we are from the true solution of the linear system, and this is how far the trial space allows us to be from the true solution of the PDE. And these two need to be in balance, because if one dominates the other, then you're either doing not enough work or doing way too much work. So if we assume that the first one decays algebraically, so like this, then this one should decay at the same rate. And because we are doing preconditioned CG with an optimal preconditioner, we need a logarithmic number of iterations of PCG. Okay, and this, unfortunately, results in a superlinear complexity. As we can see here, if we solve to quasi-optimality with our idealized parallel computer, then we have this order n log n complexity, which is not good enough. But again, taking ideas from the elliptic PDE community, we can do this nested iteration where we start at some coarsest mesh and basically alternate PCG iterations with a prolongation, a couple PCG iterations, prolongation. And in doing so, we recover the linear complexity in serial, and parallel in time, we have a logarithmic in time complexity, and parallel in both space and time. And this is, I don't know, this is quite interesting. We get this log squared of n. So coming back to the original question by Horton, van der Walle, and Worley, is it possible to achieve these complexities for parabolic PDEs as well? Our answer is yes. And we couldn't really, in the literature, find other people that have showed this earlier, although the community that looks at these kind of problems is not very large. So I don't know. Okay, so as I said, the theoretical aspect is not the full story. We have some practical computations as well. So we are solving the 3D heat equation on basically the cube. We have some manufactured solution U, which is smooth. We take a uniform discretization into some number of intervals and some number of tetrahedrons, and we discretize using piecewise linears. We have a remarkably easy implementation in Python, actually. We just use some off-the-shelf package for the bilinear forms, some other off-the-shelf package for sparse matrix vector products, and some other off-the-shelf package for distributed communication. And we run this thing, we test our algorithm by solving to some fixed target error, some algebraic error, epsilon equals 10 to the minus 6. Okay, and here are the first strong scaling results. So we see here the number of parallel processors, and here we have the problem size. So we have 16K degrees of freedom in time, 250K degrees of freedom in space, and we solve this system in 18 iterations of CG. And if you look at the total number of CPU hours, it doesn't really increase for an increase. Well, it increases only by like 10%, going from 128 to over 2,000 parallel processors. So the strong scaling is actually quite good, but the weak scaling is even better. So here we take the problem size that every processor has to do. We keep it constant, right? So at 16 processors, we have well, I guess we have 16 time slabs per processor at every simulation. And we see that the time per iteration of PCG is 12 seconds, which is essentially constant. It's almost independent of the number of processors that we have. And what was quite cool for us to see is that we can solve this system with over 4 billion unknowns in only 221 seconds, using the Dutch supercomputer. So yeah, this was my talk basically. Maybe let me conclude. We looked at some framework for solving linear parabolic PDEs in parallel, and it uses some space-time residual minimization. And we did it using a Tensor-product discretizations and a wavelet in time multigrid in space preconditioner. And we saw very nice serial and parallel complexities, this order n and order log squared n. But it turns out that the algorithm itself is also very efficient in practice, at least for the simple heat equation. Yeah, so that was it for me. Thank you.